Is the color charge distribution the same as the charge distribution? And the answer is no, it can't be, because the integral is 0. The color charge is, of course, located on quarks and gluon. So we're all here interested in the structure of the proton, the structure of the nucleon, the structure of the nucleus. And what we're doing here is a new way, I think in this community, it's a new way of looking at the nucleon and nuclear structure. And basically, it's to consider quantities that are moments of charge density operators, as is done in Maclaurin, the Gopalin model for Rick physics. In that model, observables are calculated from matrix elements of the color charge density, and the color charge density per unit area is the dominant quantity in that kind of physics, and I'm not going to talk about that. So we're sort of taking that idea and seeing what it does in nucleon physics. So I'll introduce the subject by starting with the electric charge. And what I'll say in the next 2 or 3 slides is well-known, probably.
Can I ask a very stupid question? So, in principle, you could then plot distribution of red charge.
Yes.
This is the idea.
Yes. And you won't see that in this talk, but that's the ultimate aim.
But whatever it is, if you add green and
it has to integrate to 0. We know that the color charge, total color charge on a proton is 0. So whatever it is will integrate to 0. If you think about the neutron has charge density. Its integral has to be 0. But there is a charge density of the neutron. And so this is part of the introduction. Let's see. Okay, so so going back to electron-nucleon scattering, this is just the elastic case. You have the dominant physics is one photon exchange. You have the matrix, this quantity gamma. This vertex function here is the matrix element in the proton of the electromagnetic current operator, which in quark language is just a simple thing. The sum on Q is the sum on quark flavors. And as you know, for elastic scattering on an on-shell nucleon, to calculate this vertex, you take matrix elements of this between spinors, gamma mu, the Dirac term, and I sigma mu no Q nu over 2m times F2, the Pauli form factor. And I think the only way, so we want to ask about where is the charge located, where is the magnetization density located. I think the only way to do that is in the light front picture. And so we go to a picture in which the time variable is x0 plus x3 over the square root of 2 in the current notation we're using. And then your spatial variables are x minus, has the minus sign here. And so you have x minus and r perp, and I'll use 2 different notations interchangeably. And r perp is also called v in boldface. So we want to use these coordinates, and then you can show, and I think probably Matthias had some equations like this morning when I was teaching. You can define a proton state with very large p plus, that's a transverse position equal to 0 by integrating over all perp momenta. And in that, you can take a matrix element of the charge density operator, which is really a true density operator because it has a Q plus and a Q plus dagger. So it's psi and psi dagger. This is a real density. The plus refers basically to the statement that there's a gamma plus stuck in the middle there, or alternatively, that we are projecting onto the independent components of the quark field operator. And then you can define the transverse density as the integral over all x minus. And then by doing some math and remembering the definitions of the F1 form factor, you can get this very nice result, I think, that will get a picture of the transverse density in terms of a 2-dimensional Fourier transform of F1. And so in this case here, I took parameterizations of F1 from a paper by Alberico and others, and you can make a picture of the proton transverse density, the neutron transverse density, and the neutron transverse density is actually negative at the center in contrast to simple pictures in old textbooks. And you have a non-zero charge distribution even though its integral is equal to 0, you can see that the integral would be equal to 0 if you multiply this by b and integrate over all b. So question is, can we ultimately get a picture like this for color charge density? There's many questions that I won't answer because that's why I left it as a question. Right? Now we can ask for, going along the line of electromagnetism, I can ask a more detailed question based on the first operator I wrote. Here, nope, that's the one. Suppose this is the probability operator, if you like. Then I can ask, given a U-quark at a given position, what is the probability that a D is a distance delta x minus and delta r perp away? And the way from nuclear physics, among other places, that we would calculate this, it's electromagnetic, so there's a factor out in front. You integrate over it. The first U-quark can be anywhere in the proton, so you integrate out over x minus and r perp. The proton, the U-quark charge density operator, or the U-quark density operator, which is written here. You have a similar density operator for the D-quark, replacing the U's by D's, and this is shifted, and you can calculate this matrix element. And this is another quantity to look at, which I think is very interesting because it talks about two-quark correlations within the proton. In other words, it's not a product. If you think about atomic physics or nuclear physics, it's not going to be a product of wave functions like you might get the first approximation in atomic and nuclear physics. And but to actually see this is a quantity, I think, that enters in two photon exchange processes, because you need two charge densities, so electromagnetically, you need two photons, which means that it's higher order electromagnetic, so it's hard to see. We know that two photon exchange is important in various cases measured at JLab, but basically it's hard to see. So one can ask, can we write something maybe better with gluons, because gluons are strongly interacting and you don't lose anything by having, in a non-perturbative regime, by having more interactions.
Jerry, how do you make sure that the overall operator is color singlet?
I take a matrix element and a color singlet.
So you just...
I haven't done anything with color yet. This is just electromagnetic, so this is the same.
Okay, sorry. Yeah.
Now, some other, not directly related information, but something just to point out that this is a general subject in all areas of physics. Is for a long time, people that wanted to know about nucleon correlations in nuclei. Look at the nuclear wave function. In the shell model, everything's a product wave function, but but there's no central potential in nuclear physics. There's only pairwise and three-body interactions, and so we know that there must be two nucleon correlations. That is to say, the density is not simply a product of densities. And only recently, maybe within the last 10 years, and this is an old story at JLab, people can look for these correlations in nuclei by doing electron scattering and detecting two final nucleons coming out. And the idea is in the initial state, if the particles are strongly correlated, you sort of have momentum back to back. So you hit one, it goes out forward, and the other one goes out back, and they can now detect the electron and two protons. And so we're finally getting some information about two nucleon correlations, and this is in this review article by Hen et al. And here's a picture in first quantized notation. This is the same density we had before. This is the probability of finding nucleons are separated by a distance r. This is non-relativistic, first quantized, but you have a certain operator that you can take a matrix element of in a wave function, and you can make pictures, the various, I don't want to go into this in details, but basically it's not zero, and people are making progress, and the experiment sort of looks like ab initio type calculations. So now I want to turn to the color charge density. And this is actually in the MV papers. They start, you can start with a quark operator. We take the good operator, it's gamma plus. Then you have a psi. The J is the color label. This is a color charge density, so you have the TA to your lambda A over 2 between I and J, 2 different colors, and we have some flavors. And then in general, there are gluon terms, which I think are very interesting. We haven't touched them yet, but in a complete description, you could have a proton, which is made of quarks and gluons, and the gluons would contribute to the charge density. So you could ask, what are the various matrix elements, rho A, rho A, rho B, rho A, rho B, rho C.
Jim, just a quick question. You're not only interested in objects that are diagonal in color space. So you allow different colors to quarks. Yeah,
in this case, yeah, sure. This TA is the usual, lambda Gell-Mann matrices divided by 2. So you have diagonal and off-diagonal matrix elements. But there will be always, if this is part of Kristen's, going back to Kristen's question, we'll be taking matrix elements in the proton. And calculations we have done so far involve the same three-quark wave function that Barbara was using, but we also have explicitly the color factor, the epsilon ijk. You put in the color part of the wave function. And then when you calculate stuff, all you get that survives is traces of t squared and something t cubed.
So, I mean, this first matrix element proton, rho A proton, should just be 0, yeah, but by color.
Certainly the integral is 0. I'm not so sure.
Locally, it should also be
0
because it's not a TA squared type thing. It's just a TA.
Suppose I have 3 quarks in a gluon.
Yeah, but sure, if that expectation was not so, you'd have to ask in which direction this color charge.
Okay, so this one is easy. This is 0, but this is not.
There's some funny correlation between the spatial direction and the color charge, like in hedgehog, solid one. We have that between isospin and Borg.
Yeah.
That's right. Yeah.
You don't want one color.
One color, I think Larry's answer is right. It's the symmetry. There has to be some color direction which there isn't. So,
the first one is
wait,
zero,
but I don't know.
The second one is triangle.
Why can't it look like Barbara's like this? I don't know. Could be color dipoles symmetrically around. That's obviously 0. Okay, you say it's obviously 0. It's not part of the paper. It's just speculating. But basically, the picture is that observables are computed in terms of moments of rho A. And the basic physics of what they're after is that quarks at higher x emit gluons of lower x. It leads to a lot of interesting consequences in heavy ion physics.
If you talk about quark splitting gluons, then you have to talk about the scale dependence of these operators, and they are scale dependent.
Right.
And they actually mix with one body.
Absolutely. And
operators under renormalization.
Yeah, so what we're doing is working at one scale, and in the paper we're working at a scale in which it's reasonable to use 3 quarks in the proton. And then maybe someday we'll learn how to make evolution. That's not in the paper yet.
People in multi-parton interactions or in the theory of multi-parton interactions are discussing exactly that, the renormalization of.
Oh, good. Yeah, right. There's people like Manohar writing papers on this kind of stuff. This is a particular way of doing it in terms of these moments, but so it's not unknown in physics. So my intent is to tell you what we know now, which is not yet reached all the goals that one might think. So we're using light front dynamics, and Barbara and Matthias and probably Peter also discussed this. I wasn't there, that's why I say probably. Discussed this standard stuff. So you work at the fixed light cone time, x plus equal to 0. Your r coordinate is x minus and x perp. And in the present calculation, we take our field operators and expand them out. We keep only quarks, neglect anti-quarks. You get, this is the density operator. Now, in looking at this expression, you have an overall P plus. You have an exponentials. plus component of the momenta q and p are always written in the light front wave functions. It's xq times p plus or xp times p plus. And we can take the limit as p plus goes to infinity. If you look at this thing, it oscillates like crazy. So it tends to average out to 0 if you're doing integrals. If you're more careful and you put in a test function that's in the appendix of the paper, I'm not going to discuss it here, you'll get that this is simply 2 pi times the delta function of xp minus xq and delta of r minus. And then the correction terms of order 1 over p plus, 1 over p plus squared, and so on. We just keep the leading term. And putting this delta function, taking this limit for the p plus factors that are in here, you end up, well, first of all, you have a delta function in r minus, I should say that. So that means you literally obtain a pancake shape. This is coming from Lorentz traction of an object moving very fast in the plus c direction. So it literally is a pancake shape if you take the density operators. And so our rho can be written in coordinate space as in here. It's contracted, and then you can take the Fourier transform. Here, k, we neglected the perp part, but the k perp is canonically conjugate to the x perp. So you can work in momentum space or position space, and you have these density operators. And
I don't understand why you have this product of delta functions.
Well, if you're taking a function of r minus and integrate, then
you have this combination of x times r minus.
This is really
Well, the best way to see it is to integrate on both sides of the equation over r minus. Then on the right side, the delta function goes away. On the left side, you use the well-known equation that an integral or an exponential function gives you a delta function.
Yeah, this is in our appendix. So actually, you have to do it with a test function. What Matthias said is exactly right. Now we're going to take matrix elements in plane wave states, and we're going to take expectation values, and these states are normalized to delta functions in momentum space, right? So we define an operator, the expectation value sub k plus means that you have a fixed p plus because the operator doesn't shift any of the pluses. We're going to take the O is going to be not just rho, but rho squared and rho cubed and so on, and we divide out by the normalization. So in every calculation we do, in the top part, there's always a factor of k overlap with p. So you have infinity over infinity, which cancels out. That's all I'll say about it. So we evaluate matrix elements. We use a light front wave function. And the general formulation is given, in sort of a book chapter by Brodsky and Lepage, and then formal paper, Brodsky, Wang, and Schmidt, I think. And then there's a nice expression in Yuri's book with Levin. There's a nice textbook type explanation of light front wave functions. And I think it's really the only way to have a light front wave function. To have a wave function in quantum field theory is to light front language, and I don't think people here know that. So in our first calculations, we use simply a 3-quark flux space. The matrix element we actually calculate is definitely 0. There's no mistake about it. I don't know what it would be. People are telling me the answer that it would be 0 if I had 3 quarks and 1 gluon, but that's not in our paper. So I'll leave that as a question. And so we calculate the first one that's in our paper that's not 0 is to take 2 rho operators. Rho tilde is the one in momentum space. Shifts each quark momentum by q. Q is the momentum with the sign convention used to see emitted momentum. We start out with this notation again. I'll remind you, we start out with 0 on the right side. K perp is 0. The perp component of the initial momentum is 0, and then there's a shift of K perp. And there indeed are 2 terms because these operators in the first quantized notation, each row is a one-body operator. So you can have, this corresponds in a pictorial language to gluons being emitted on the same quark or on two different quarks. And so this term we call G1, and this term we call G2, and they come in with the minus sign between them. That minus sign is demanded by the color singlet nature of the proton. The G1 is this is just like a one-body operator, so the integral you would do is just the same as you do in calculating the form factor, except you have this color factor instead of the charge factor, so that's very straightforward. An interesting limit is the forward scattering limit, in which you take k perp is equal to 0, and in that case, this form factor G1 is 1 by the normalization integral of the proton wave function, and you get 1 minus G2 of k and 0. G2 depends on two momenta because two different quarks are involved. It's the analogous thing of the two-body density that they talked about in the non-relativistic limit. Especially interesting to me, and I think it's sort of a check on the calculation, if you take this momentum to 0, then G2 has the same normalization expression as G1 does, and no momentum coming in. So you get 1 minus 1 in the limit that k is going to 0, so that's 0. And we'll see that this is coming in the calculation from the color neutrality, and we'll see that this is important in suppressing infrared divergences. But this kind of cancellation is known widely. It's basically the same thing, the reason why you have color, why you have the potential to observe color transparency, and this calculation is also, this cancellation, I think, is the basis of proofs of factorization theorems. So in a model wave function, one can do a numerical calculation and calculate the quantity G as a function of k and GeV, and it really starts out at 0, and then this behaves more or less like some kind of slightly different form factor, two-body form factor. Also appeared in a paper by Soper and Gunyon. And this one goes to 0, so you asymptote out to 1 fairly quickly. There's a hole in this form factor, and sort of the width of the hole is determined by the proton size and momentum space, 1 over a quantity closely related to the radius of the proton, and I emphasize the cancellation. Okay, questions?
Just one comment. I mean, it's very natural that at large k, the predominant coupling of the two operators is to a single quark, because you short circuit the momentum that is much larger than the typical momentum.
Right, exactly. Exactly.
And that was used previously in the modeling of GPDs, like say the wave Frankfurt Strickland model GPDs at small x, is they couple the two gluons to the same proton.
Right.
And then you just have a KT much larger than the soft KT in this last. Right.
So you're in this regime, you just use 1 and you're happy. Yeah. But if you're in the infrared regime, then you're not so happy doing that. Then you have to deal with that. So the first test calculation is let's see what we get in the simplest limit possible. Calculate the gluon distribution in a proton. So this is all in Yuri's textbook, but it comes out in our calculation too. You use the lowest order Yang-Mills equations of QCD in the light cone gauge. In that case, you use the Poisson, basically Poisson's equation with color charge. And the FA plus I, which is the quantity that enters in the gluon density, goes as Ki over K probe squared times the densities. It's exactly analogous to E and M. And the gluon distribution involves the matrix element of the square of this, F plus I, F plus I. And then when the dust clears, you get that xg of xq squared, you get some color factor and an integral from 0 to q squared of this very same form factor that this combination enters. K is equal to 0 because we're calculating proton to proton, no momentum transfer. And what naturally comes out of this calculation is that you're getting a 1 over k squared, which is the residual of having a 1 over k to the fourth. And after doing some integrals, and this might tend to, in the lower limit, might tend to give you infinity, but you have this cancellation, so you have a cutoff coming in naturally from the calculation, and the cutoff parameter is closely related to the size of the proton. And at large q squared, you can simply get the log. And I think this is a well-known result. I was surprised by this because it doesn't depend on x. You can get the x by doing evolution in higher order terms. That stuff is well known. So things look good. Then a similar thing happens in J-psi production. So we have two gluon exchange in J-psi production. There's a top part and a bottom part. You have this is a photon wave function that goes into, say, a CC bar. And the CC bar on this side gets tied up with either, let's say, a J-psi wave function or an excited psi wave function or whatever. So the top part here has the conventional factors, the light front wave function of the photon, the virtual photon. Then you get the Q-cube law wave function, which is your J-psi wave function, and some momentum transfer factor, and this gets tied in. You have to attach, you attach these lines to these lines in the proton, but you need the two diagrams, and that so you get an integral over some transverse positions of an operator T of R, B perp, and K perp, and basically I just point out the essential things in the equation. You're integrating on Q1 and Q2, where Q1 and Q2 refer to these two momenta. And you have these are the propagator factors, 1 over Q1 squared, 1 over Q2 squared. And you get really 4 terms, but 2 of them combined. This is terms when you land on the same guy. And these are the 2 terms when you land on a different guy. And then you have this form factor, the same one that we had before. I think that's a typo. This should be just a G. I have to change that. The G goes to 0. Anyway, there's no singularity if either Q1 or Q2 or both, if either Q1 is 0 or Q2 equal to 0 or both are equal to 0, there's no singularity. Things are well behaved. And one needs both diagrams to get this finite result in your matrix elements. This is, I think many calculations in the literature of J-psi production do not respect the color neutrality of the proton, and it has some other kind of cutoff that comes in a phenomenological way. But this it just sort of comes out of the calculation. Of course, we didn't do any numerical work yet.
Jerry, not in the exclusive case, which you're considering.
Not in the exclusive.
In the exclusive case, there's a factorization.
Can they do this?
For
okay, fine.
Vector meson production, which includes J-psi photoelectric
okay,
production.
So this is not so new.
And the 2 gluons couple to the gluon GPD in the proton. So at the end of the day, when you average over your wave functions, and the sum of the 2 terms coupling to the same constituent to different constituents, it just gives you an effective one-body density, which is the GPD, which is all that you're. I
don't know if this is a GPD. I wouldn't call this a GPD because it's gluons. GPD is photons, so many factors are different.
No.
It's a gluon GPD.
Exactly the gluon GPD.
It's a gluon GPD.
Yeah.
Is also forward.
But I mean, if you consider the J-psi production, then the kinematics requires that it be off forward.
Yeah, this is off forward. We have a K perp here. Okay. Maybe this is not relevant. Okay, so we can do the same thing for the 3-quark color charge density. And then there are 3 types of terms, all the 3 gluons from the same quark, 2 gluons from the same quark, 1 from another. There are 3 such terms, and each gluon is emitted from a different quark. And one of the terms, One of the terms is interesting. If all three gluons are in the same quark, we put a superscript 1.
I'm sorry.
It's a good thing you're not in my class. Anyway, I have only 17 slides. I'm really done. So this has a symmetric component which goes as the anti-commutative thing built out of anti-commutative DABC over NC, and we call that the autoron form factor. And the three gluons can be an autoron. They have charge conjugation -1. That is, when they couple, when these three gluons couple to the QQ bar on the top, switching the quark and the anti-quark at the top gives you a minus sign. So that's known to be called the autoron. And so, in our calculation, the three gluon exchange contributes also to the J-psi production. And the three gluon exchange also contributes to A to C productions.
Not for deep side.
What?
Not for deep side.
Yes, it does.
So how is it possible?
Because the orbital angular momentum of the J-psi relative is nothing violated by it. It's in many papers in the literature.
For A C, yes, but the deep side has different quantum numbers. It's like Rho-meson. So you have two, so charge conjugation in T channel is plus, not minus.
I think we had a discussion at BNL, and was the conclusion that three gluons can be coupled to charge even and charge odd.
Yes, that's what I thought.
True, but de-arrangization,
I can't hear.
It's complicated, but not inside in my.
I think it does contribute. We have the calculation in the paper.
I have a doubt on that. So can you go back one slide?
Sure.
So you have an integration of R and Z, right? Or maybe
Where?
The next one. Oh yeah, this one. So you have an integration of R and Z. So
right.
So change variable from R to minus R, and at the same time change variable from Z to 1 minus Z. And if you have a Holderon coupling to J-psi, do you get the same integrand?
Yes, I think so.
Did you check that?
I think Adrian checked it.
Okay. It's this.
You think it's strange? Okay, I'll look at it again. Certainly, the three gluons could have even or odd parity.
That's I agree.
I must say I didn't understand that. Anyway, so now I'm at the last slide. So I think we have a new way of looking at the proton structure. And the new way is to use moments of the color charge density. And we actually constructed using a simple three-quark light wave function, the quadratic and cubic correlators. And one could have more complicated wave functions and do more. We think that the quadratic correlator corresponds to the pomeron and the cubic to the autoron. And I think this is complementary to the GPD formalism. It's a different way of looking at it. And maybe it can be developed into a more realistic picture. Certainly, it's not as advanced as the stuff we saw all day this morning and this afternoon from the other speakers, but it's an interesting way of looking at it. And it closely, I find it interesting also that it closely mirrors progress made in understanding the nuclear wave function in terms of two nucleon correlators that people are now measuring, and they're hoping to measure three nucleon correlators. So thank you.
Question for Jerry?
Jerry, is there a particular region in X where you would say this is a reasonably good picture? It's a large X, small X, or it doesn't matter?
That's a very good question. If you look at there's different X's that are involved here, right? And so there's the x, the variable x comes up a lot. It refers to the momentum fractions of the quarks in the proton and also the actual x of the virtual photon. So I'm not sure which you mean, but I guess it's the x of the photon. Is that right?
Well, typically what parton x.
Okay, parton x, we have this three-quark wave function, so clearly it's not a
So
good
it's
wave
large.
function. Would not give you the correct PDFs already for very low x. So, but that I think
But
is
you
not.
could still talk about color density correlations.
Yes. That's right. This is a property independent of the probe. It depends just on, as defined, it just depends on the matrix elements in the proton. So if you have a better proton wave function, you get better results for the rows. For the correlated, 2 rows, 3 rows, that's what you're going to get in the proton. And the better your wave function is, the better the matrix elements are.
Except for this issue of scale dependence of your operator.
Yes.
This is not like a twist-2 operator that renormalizes
Right. So
into
the
itself and has a,
renormalization.
like, weak scale dependence. I mean, your operators have
Right.
a massive scale dependence and they mix with one body operator.
Yes. So that, in a complete formalism, which this certainly is not,
you can get
you
results
would have
at
to
some
put that
scale.
in. Right now, we're saying that we're working at some scale where it's not crazy to say that the proton has 3 quarks. And then to go beyond that, that's a future paper. I don't think that it's impossible. I think it's a lot of detailed work that could be done. I think it could be done, and then one would have to, you know, parton distribution is scale dependent. These things are scale dependent, but they're still interesting. And we want to know. I mean, if you really want to know about the structure of the proton, we saw how many things there are about the one-body operators that Barbara was just talking about, but you can have 2-body operators. And you asked about how, this is really where the dynamics are. What are the 2-body, what are the matrix elements of the 2 densities? What are the matrix elements of 3 densities? I think they may be ultimately clues to the underlying dynamics to really understand confinement. I think this is a new way of looking at it. How we can relate that to experiment is still, I think it's quite, that remains to be done. We certainly haven't taken those steps. But, going back to the nuclear physics case, it's possible in nuclear physics to do it. So it should be possible in quark physics when you have the, you have a tremendous simplification of the very high energies, which really simplifies the probes and allows the impulse approximation to be much better than it is for nuclear physics. In nuclear physics, they couldn't make progress. They didn't have high enough energy probes. And here, what we're talking already, we have high enough energy probes.
Well, I think that the whole picture is tightened extremely to using a light cone gauge.
Yeah.
And therefore, your probe operators are actually essentially non-local. You have some complicated thing because it's the object that you consider is gauge dependent. If you want to work, for example, in covariant gauges, your operator just one.
Each row is a local operator. Each moments of the rows, the row is a local operator.
That was it. Your local operator will mix with the Gluon field and anti-ghost operator. So you will have also the correlation function of ghosts. So you will also have to introduce the ghost distribution.
The ghost distribution.
Yes, what you want is not, I don't know, but you must because your gauge non-invariant operator will mix with all operators, and
row itself
row
itself is gauge invariant.
No, you have a index gauge. You have a color index. You have a color index. You have an operator which is not gauge invariant. You will nicely mix with all gauge non-invariant operators of the same dimension. So I will suspect it mixes very well in covariant gauges with for example,
Yeah.
Gluon field and anti-ghost, something like this.
Right. So I come at this from sort of a JLab perspective, but a lot of these questions.
There are no ghosts at JLab.
There are no ghosts at JLab. Not even a Halloween ghost. But what I want to say is this McLaren-Gopal picture has been in the literature since 1994. And people have studied a lot of things that I don't know about. They have studied evolution and they've studied all the various corrections. And I think a lot of the answers to these questions are in the literature.
But I think implicitly, well, that's what I said, that implicitly imply that we are using simply light cone gauge. And actually, you simply have this vertex that you have. It is a core Gluon vertex when you just strip off the Gluon propagator. Yeah, so this is, if you consider just the distribution of Gluon of the operator G plus perp, you will just have your construction plus two additional propagators. And this would be the usual picture. Simply strip off these two Gluon propagators.
Right.
Yeah, so you have this, essentially you have two Gluons in axial gauge. And they couple to quarks through this vertex that you introduce. In this sense, it's just another way to say more or less. Just two
well, I think the example I gave was certainly
two Gluons with when they multiply by inverse property. So this is
that's the basic thing in this model. You get this emission.
Yeah, but what they say, you have to consider physical Gluons, which means that you essentially think you have to stick to the light cone.
Yeah, that's fine with me. That's fine with me. I have no problem using the light cone gauge. I see too. Peter's going to stand first, I think.
So if you, it sounds like there should be also probability densities in some sense, in the sense that you have like conditional probability to find the way you introduce a certain parton of some color if you found another parton of another color. So did you already look how to check or prove or demonstrate that there is this positivity for such a probability? I mean, I don't know exactly what of your correlation function, but in some sense this can be formulated in such a way.
Yeah, I don't. Certainly, the rho is related to a probability. In the nuclear physics language, there's a two-body density and a three-body density, and it's not positive. I think it's not necessarily positive definite. There's two-body densities, three-body densities. Well, I think they are positive definite. Yes, they are positive definite.
It's obvious.
Yeah. Yes. I'm curious.
It's basically just a comment. It's related to the last bullet point and also related to what Christian said earlier when you talk. So if you talk about the object with the two rows, you have an expression for the amplitude for shape side reduction. At the same time, you have an expression for the amplitude in terms of GPDs. So maybe the way to look at this, maybe you have a somewhat maybe model dependent way of resolving GPDs.
Or a more microscopic model of the GPDs that the two Gluons coupled with the same quark or different quarks.
So that could be interesting.
Yeah, I think, it seems to me that the difference, I mean, I don't, in the two Gluon GPDs, if they're similar to, if they haven't studied, if they're similar to quark GPDs, it's the Handbag diagram, right? So it's the same.
It's a Handbag diagram, and usually the logic is that, say, the Gluons coupling to the Jape psi have transverse momenta of the order of the inverse size of the Jape psi, which is related to the heavy quark mass. So they're much larger than the inverse size of the nucleon. And therefore, the coupling to a single quark is preferred.
Yeah.
Short circuit that hard momentum. And in fact, that's how the Gluon GPD is usually modeled at even at small x in calculations for error that you take two gluons coupling to
Right.
to a quark and or to a quark or to themselves to a gluon, which actually has a bigger cover charge at
Right. So let's say
small x, and
right.
that's how you get your GPD. And then
Right. So I think that let's say that these photons are gluons now. Then this is the usual handbag diagram, which is the GPD. The Cassier's diagram is that. I think in general we'd have to put both of them together at the same time. But if the gluons are hard, this diagram goes away, and one is left with the GPDs. I think that's what you're saying, right? This gives a possibility. This basically is a different picture. Looks different, but this is really the Cassier's diagram, scattering on two different quarks, and in a situation when one of the momentum becomes soft, these two guys cancel, avoiding trouble, and therefore you don't have an arbitrary parameter coming in.
I mean, if you like to single out Cassier's diagrams or say four quark correlations, there are some special operators that appear only through four quarks, which are change the isospin by 2 units. So I would say, imagine you have say U bar D, then you each U bar D changes the isospin by 1 unit, and then together you change it by 2 units, and there's no one body operator that does that.
Right. So,
if you like, you could look at a matrix element of that, say, isospin 2 4-quark operator, for example, between like sigma hyperon states, where you can have transitions between with delta I equals 2, and then it would be protected from mixing with one body operators.
I think to me they come along, and in the examples we worked out with the couples being gluons, they cancel in certain limits.
Did you check in this graph when the gluons coupled to different quarks that what you call wave function? There's no hard scale in it.
Yeah, it's a light cone wave function, so it has really basically one parameter. Or, like
in general, yes, but I mean, at least if you have a larger momentum transfer for this graph, then you need an additional gluon. This is a part of the Brodsky-Gepard picture.
Yes, I don't understand the question. I mean, this is we just calculated this.
Have that. And so far, if we don't have an additional gluon exchange between the two quarks there, then they are hard scaled.
Okay, now I understand. Now I understand the question. You say there should be a gluon here.
Not there, not there. In the other graph, but in this graph.
What Peter is saying is, I think, if the transverse momentum of the gluons are of the order of the nucleon size, then you can have both graphs at this, in parallel and add them. But if the momenta are much larger than the nucleon size, then it makes no sense to add them. You have to add an extra part gluon exchange to the right one.
Right. So we're working with right.
We're definitely
working. Let me finish. Let me answer the questions. So definitely we're working to this order. But if the gluons are really hard, the wave function will kill the contribution, because we're doing exclusive proton going to proton, and the wave function will kill it, I guess. We have these form factors. Of course, the calculation is to this order, and you could put gluons. In this formulation, you're calculating the matrix elements of in the right kinematic region. This is the correct way to do it with moments of rho. And we haven't quite worked out how that connects to EIC physics.
With adding additional gluons, it would still be suppressed, and you would be left with the handbag diagram, which is what Jerry said half an hour ago.
I see. Yeah,
Can I ask?
Sure.
Those gluons, okay, which couple the quarks down, okay, are they iconal or not?
They're not necessarily iconal.
So
at the moment, we just put them in with gluon couplings with propagator is 1 over q squared, and
No. I am talking about numerator of propagator.
the numerator.
Numerator. This is for me.
The numerator, we have always the gamma plus. So in that sense, it is iconomer. I think if I understand your language.
So this is like, this is because of color glass compensate. Like
This is the color glass, yes.
Of course. But so then there is no such a question to have exchange, okay, between two quarks. Okay? Because this kind of, this is iconal coupling, okay, and such a simple, all possible exchanges are simply needed, okay, for this written for gauging value. Okay?
Yes. Yes.
So
yeah, the row has a gamma.
This is similar, okay, in different language of what Bartels. Johann Bartels.
Okay.
I am not completely that. Because spirit is small x, okay, and this is exactly. There is a paper by Bartels and Motika, okay, and you would see, okay, similar. Bartels
and who?
What?
Bartels and who? You said there's a paper?
Motika. I can give you.
Send me the reference. Good. Yeah.
Can you clarify what exactly you mean by iconal? I mean, probably the polarization state of the gluon that is longitudinal or transverse. And you're saying it's longitudinal?
Yes. This is what is called nonsense.
Yeah.
It's non-polarization. Because it's vertex.
Is that, Jerry, is it really longitudinally polarized gluon?
I don't.
But then you couldn't calculate the gluon density. You just calculate the gluon density, which is the density of transversely polarized gluons.
Let me make this statement. We have the gamma plus operator, so the quark propagators are iconal. That's enough, he says. Okay, good.
No, you're asking about the gluon.
The gluon certainly, you can't have, where are they? This is what it is.
That's transverse polarization. That's the operator that goes into the leading to its gluon density.
Yes. But the quark propagators are gamma, they're basically, you always have a gamma plus everywhere.
The question of how the gluon is emitted. The question is how let's say, what's the gluon polarization measured at the upper end?
I have no idea.
Okay, this is okay. Also standard answer, but okay, in the language of small e's. Okay, so first you have an iconal coupling, yes. Okay, but then okay, in small x, okay, you have only transverse momentum of this gluon, okay, which is attached, okay. And if you require, okay, gauge invariance of this object which you calculate, you can trade, okay, contraction of gamma plus into k transverse, okay, and you are getting the suppression and vanishing of let's say this form factor. It's okay. So, but then I am saying, in my opinion, there is no for J psi. Okay, absolutely, I don't see having iconal coupling. I do not see possibility to have a three gluon exchange.
Okay, we'll have to look at that.
But this formula is in which page? Which page is this? Because this is written for this nonsense polarization.
Yes.
But
upstairs, okay, this
can it be consistent with using like gauge?
It is kind of you can use okay in small x, okay, well also what the color glass they are doing. If you have an amplitude, okay, if you have two blocks, okay, you can use okay for one the upper blocks one axial gauge, okay, and this is okay, and the bottom another.